Okay, welcome to the 13th class meeting of the spectrally correlated random processes. By the way, let me check the audio. Check. Okay, everything works. So last time we've seen this paper without the impropriety assumption of the interference reduces to a very simple problem, which is well known. In order to understand that, these are what you need to know preliminaries. First, you need to know what is water filling procedure. When you have parallel Gaussian channels. So the problem looks like this. So you have possibly vector valued input x, and you have, so I'd rather not say this, x1, x2, dot, 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 xn, and you have additive noises. This is not good. Okay, let me use m, l, l, okay. And you have the outputs. So our assumption is that some power is less than or equal to P, and Ni's are independent, and each Ni is complex Gaussian with mean 0 and variance sigma I squared. And we assume these sigma I squared are all positive. And then what you want to do is to find the optimal input distribution that maximizes the mutual information between the input vector x, that is the collection of all the x sub l's, and y vector, that is the collection of all the y's, subject to this power constraint. And the reason why the optimal solution is called water filling procedure is this one. So suppose this is L-axis discrete. So you have first, second, and up to capital L channels. And what you need to do is to mark the value of sigma sub I. So this height is sigma 1 squared. This is sigma 2 squared. And that is sigma L squared. And the procedure includes this part. You find some value nu that makes the difference between this nu and this height of the noise. So nu minus sigma sub I squared, and its positive part. And that serves as the height of water level. So if sigma sub 1 squared is greater than nu, in this case, this summand is 0, right? So that is 0. If sigma sub 2 squared is less than nu, then this argument inside the positive part is non-negative. So this difference serves as the depth of the water. from surface to the bottom. And here, this serves as the value. And each height is actually P sub 2, P sub L. So in this case, in this example, if this P sub i's satisfies this condition, then P sub i's are allocated powers. And actually, what you need to do is to find the level nu. And this is very similar to water filling. So consider you have some basin with bottom look like this. So this serves as the sigma sub i's. Now you have finite amount of power, in this case, amount of water, P. Now you pour the water under the gravitational pull. Then there will be a flat surface and the entire volume of water, in this case area, will be P, right? And here, this level serves as nu, and this height serves sigma 1 square, sigma 2 square, something like that. So finding the unique water level nu that satisfies this equality is the same as water filling in our real world. That's why this procedure is named as a water filling procedure. Then the final capacity, bits per channel use, parallel channel use, becomes the summation of log 1 plus P sub I sigma sub I squared. Here, the base is 2 because we have bits per channel use. And be careful, since we assume complex Gaussian noise, there is no 1/2 here. Ready? If we assume real Gaussian, then we must have 1/2. Anyway, so this is the water filling procedure. And I believe most of you learned this procedure in the information theory course. And then, so this is first one. Second one is the singular value decomposition. As I told you, singular value decomposition, which I do not have enough time to cover all, gives you very interesting transformation of a rectangular, general rectangular, complex valued rectangular matrix in this form. First, H is assumed a complex m by n, then U is complex m by m, and sigma has the same size as H, and V is n by n, and especially U and V are unitary matrices. Actually, we intentionally restrict when we find this decomposition, because such a decomposition could be infinitely many. What we do is that we enforce the first factor and last factor as unitary matrices. And also, we enforce this sigma as what? Not general complex, but non-negative real. Got it? By the way, if I put plus in the subscript, which means that non-negative real, if I put plus plus in the subscript, then it's strictly positive real. So sigma is intentionally chosen to be a non-negative real. And also, each ij component is what? Sum sigma sub ij squared delta ij. So what does that mean? Only when I equals j, you may have non-zero component, and that is sigma sub ii squared. Or if you want, you may just say sigma sub I squared delta ij, where delta is the Kronecker delta or indication function. When I minus j equals 0, then you have 1 and otherwise 0. Got it? So sigma square looks like something like this, something like that, or if it is square, then something like that. By the way, this diagonal line means possible non-zero values, and all the other off-diagonal entries are zeros. And in order to find this one, what do? Let me just remind you what you learned in graduate level linear algebra. You consider H Hermitian transpose, which will give you Hermitian symmetric positive semi-definite matrix. And also you consider Hermitian H, which will also give you positive semi-definite Hermitian symmetrical matrix. And then actually what you do is that you utilize the well-known linear algebra fact that if you have non-negative Hermitian symmetrical matrix, eigenvalues are all reals, especially for positive semi-definite, you have non-negative reals. And that may serve as the so-called singular values here. And while you also apply the eigenvalue decomposition to each one, for the Hermitian symmetrical matrix, you may find what? You may find eigen decomposition where eigenvectors are orthogonal and having unit values. You can choose such eigenvectors. That serves as the left singular vectors and right singular vectors in the U and V, and that gives you a complete view of singular value decomposition. By the way, last time I've given you a very, very, very simple decomposition where you may have arbitrarily many different decompositions, right? Let's just consider very simple. Very simple matrix like this. Then you may introduce any arbitrary e to the j theta and e to the negative j theta, e to the j theta 2, e to the negative j theta 2, with arbitrary theta 1, theta 2, theta 3, and give them to u and v. In that case, you definitely have non-uniqueness of singular value decomposition. So mathematically, precisely speaking, SVD it does not give you unique decomposition, but in some sense of phase rotation and how to say that, reordering of singular values. Accordingly, the reordering of left and right singular vectors, you have kind of equivalence classes. In that sense, you may have, in some cases, with distinct singular values, you may have identical unique decomposition. And if you just want to do not be that precise, then you may just consider subspaces spanned by each eigen singular vectors. In that case, you may say that, okay, the singular value decomposition provides me a unique set of subspaces and corresponding singular values, something like that. So SVD applied to this model Here, H can be a rectangular matrix. Then you have U sigma B Hermitian X plus N. Then what do? First, you may apply U Hermitian to have this one. Now, you know that unitary transformation does not change the length of a vector. What does that mean in the statistical sense? When X is zero mean, some variance, zero mean and IID, then you have this X tilde is also zero mean IID Gaussian, something like that. So what you do is that first, you set this is Z and this is X tilde, then you have sigma X tilde plus N tilde. We assume N tilde is U Hermitian N. Then what is this one? This is a very similar to what we had in these parallel Gaussian channels. The only difference is that since the length of X tilde and Z may be different, we may have some strange cases like this. So X tilde 1, X tilde 2, X tilde N. But here, if N is 1 less than, so M is less than N by 1, then you have here what? 0 multiplied to the input. So that channel input is not contributing to the output. In that case, you do not assign any power. So P tilde N must be 0. By the way, since we have V here, we don't know yet whether we really do not utilize one of the channel inputs or not. It depends on the form of the unitary matrix V. However, one of the dimension is not utilized in this case. Got it? So anyway, by combining the water filling procedure and singular value decomposition, you can find the capacity of a MIMO channel, multi-input, multi-output channel, which is in particular discrete time memoryless channel. The difference between our case is that we have continuous time channel. So we need some integration to compute the capacity. And that is also, if you remember from the information theory, you remember the frequency domain water filling when you have additive colored Gaussian noise channel. So anyway, to fully understand the preliminaries, you need to understand what is water filling for parallel Gaussian channels and its extension to frequency selective channel, continuous time channel, which will give you how to water fill in the frequency domain. And again, you need singular value decomposition. And finally, as you learned in this course, you need to vectorized Fourier transformation. In particular, you choose the Nyquist zone, length of the Nyquist zone, the same as the inverse of the cycle period of your interference. In that case, what do you have? Your additive noise becomes Y sense stationary vector random process. Of course, as will be shown in one of the subsections, you may choose twice the cycle period. In that case, you may have twice as many as the output numbers, but all the capacity is preserved, and actually your water field solution is exactly the same in the sense that your input distribution of the continuous time random process have the unique distribution. Anyway, these are just simple applications of many parts from the already known or simply extendable results. But as I told you last time, what is the key? Here, the noise is not assumed to be proper. We have improper cyclostationary Gaussian random process. So let's focus on that. N of T is improper complex cyclostationary Gaussian random process with cycle period a positive number T. Okay? Now, what can you do? Up to this paper, this topic of stationarization of such a random process didn't appear. So let's make it more general than this one. So here, double parenthesis G means generalized. So let's consider x of t is a second order, means finite power, improper complex, Y-sense cyclostationary random process with cycle period t. So actually, in this paper, we also assume the finite power of the noise. So the only difference is that let's consider general random process, not restricted to Gaussian. Then the question is, how can we stationarize x of t? If x is real, Y-sense cyclostationary, or if x is proper complex Y-sense cyclostationary, then there are two methods. One is to utilize the harmonic series representation of such a random process, and the other is the translation series representation, which we haven't yet covered, but will soon cover. And I myself named this transformer based on the harmonic series representation as vectorized Fourier transform. But we know that that works only for proper complex random process case. So let's remind us what was the vectorized Fourier transform. So here we multiply some complex exponential function with integer multiple of the inverse of the cycle period. And we have many branches with uniformly spaced, plus. My convention is that the first one has negative L. No, positive L. Sorry about that. Yeah, positive L, and here, negative L. So basically, we have two capital L plus 1 branches. Then each branch have the theoretically ideal low-pass filter with cutoff frequency, the half of 1 over t. So this is the vectorized Fourier transform that converts a band-limited signal. Here, our assumption is that L must be chosen to cover the entire frequency band of the random process X. So suppose this is the power spectral density of the input random process X of t. Then what do? We first choose the first Nyquist zone of length capital T, and then we add two more Nyquist zones, two more Nyquist zones, two more Nyquist zones, until we cover all the spectrum having non-zero power of the input. And this finiteness is because we assume X is of finite bandwidth. Actually, you may generate a sequence of random processes if X is of infinite bandwidth. So it's theoretically possible, and you may not believe in mathematics department, you have some linear algebra with infinite length vector and infinite size matrix, and you do almost the same thing as matrix vector multiplication. So you can do the same thing for this vectorized Fourier transformer if you have band unlimited signal. However, anyway, for an information theoretically optimal results, usually we need band limitedness, strict sense. Otherwise, we may not well define the capacity of some channel. So anyway, we have finite L. So let's see. So this part will have center, if I remember correctly, L hertz. And the last one has capital L over T hertz. So the first branch actually shifts this entire spectrum to the right side by capital L over T hertz and apply strict band limitedness. So this one is not precise, but this one shift up to the baseband corresponds to x1, x of 1 of t. And similarly, the last one, actually the part of x of t that corresponds to this band, this last Nyquist band, corresponds to the output of the last entry of the vectorized Fourier transform, because last branch shifts all the signal component to the left by L over T hertz, and then applies the strict band limiting filter. So you have this part, it's not exact, but that part appears at the last branch. And all the branch outputs are strictly band limited in this case. Got it? So we may choose common frequency f for these things. And what happens? These components possibly have correlation for the same frequency location. Because if X is Y-sense cyclostationary with period T, we can show that this vector random process is Y-sense stationary. So different frequency components does not have any spectral correlation. Got it? Now, before we move to our new vectorized Fourier transformer that stationarizes improper complex random process, let me ask you a question. Then, last time I talked about the bandwidth, effective bandwidth of the channel when we use vectorized Fourier transformer. And I said that that is related to the excess bandwidth. So the average dimension is 1 plus beta. And let's see why that is true. In order to understand, let's see an example of some cases where we have raised cosine shaped power spectrum. Suppose this is the bandwidth we are interested in. And we use 1 over t as our cycle frequency or inverse of the cycle period. Then let's first find the center Nyquist zone. Then here we have the Nyquist zone that ranges from negative 1 over 2t to positive 1 over 2t. So this is the Nyquist zone. And next is these two. Next are these two. So we have capital L equals 1, right? So basically, our vectorized Fourier transformer will give us length 3 random process. However, suppose we consider them in the frequency domain. Then let's see what happens. For the offset 0, this signal component and that signal component and that signal component will appear. However, we said signal is band limited to plus minus 1 plus beta over 2t, which means that in effect, even though the signal appears to be three-dimensional in the time domain, in the frequency domain, what? For f equals 0, you have dimension 1. So let's say d of 0 equals 1. Now, we consider different offsets. So let's move this dot, and this dot also moves up to that point. So when you move by adding positive frequency value, this will never contribute to a new dimension. However, think about this point that moves, and suddenly here you may have some signal component within our band of interest. So what happens is that if you move this point by how many? Beta over 2t, I believe. Then suddenly this point moves up to here. Am I right? Yeah, I believe so. And then you have actually 2 dimensions available. So Similarly, you have the symmetry. So if you subtract some positive value of f, then what happens? Still, you don't have anything, but these points becomes inside the frequency band. So you have two dimension. So what you can do is that you construct some function d of capital D of f and d from negative 1 over 2t to positive 1 over 2t is inclusive or exclusive. It doesn't matter in the major theoretic sense. And to the integer. And this value gives you in the frequency domain dimension of the signal. And what do you have? You interestingly have in our case of that beta between 0 and 1, you have what? 1, 2, and 2. Now, let's calculate the average value of this one. So what you do is that you integrate and divide by the length. What do you guess? You have exact 1 plus beta. And this example can be generalized to any value of beta if you want, beta greater than 1. And your dimension may become larger than 1 and 2. But on average, you always have average dimension the same as 1 plus beta. In that sense, you have that as the average dimension in the signal design. Got it? Anyway, you will see that derivation in some of the papers in our reading list. Now, here goes the properizing frequency shift vectorizer. Just a second. Did I name it here in this paper? Just a second. Yeah. P fresh scalarize. P fresh vectorize. Okay. Yeah, name does not have consistency, but anyway. Just a second. Vectorized Fourier transform. Second, VFT. Yeah, I named the transformer incorrectly, actually. Here, this shouldn't be named as VFT. Yeah. Okay. It seems that so far I called the transformer as something different. Let me rename it. Okay. Yeah, I got confused. I'm very sorry. This is called fresh vectorizer. Because there is no Fourier transform yet. Got it? Yeah, I'm sorry about that. Vectorized Fourier transform means that we not only vectorize but also apply Fourier transform at the output, but that is not true. Okay, so this is fresh vectorizer, and fresh means frequency shift. I didn't name it. Dr. Gardner, who is one of the pioneering explorer of the cyclostationarity, coined this so-called fresh frequency shift. So this is fresh vectorizer. I'm sorry. So we have frequency shift component and band limiting components. That's why this is called fresh vectorizer. Yeah. So here we have proper rising fresh vectorizer. By the way, I used the name of this transformer incorrectly even in the first take-home exam. I will modify that in the updated version, which will not be given you. Anyway, so here the idea is very interesting. If I just tell you the result, this P-fresh properizing fresh vectorizer has very similar structure as the original fresh vectorizer. But it not only generates the vector valued signal, but also the input that is improper now becomes at the output proper and also stationarized. And let's see its interesting structure. So suppose you have a random process Y, which is improper complex Y-sense cyclo stationary with period capital T. Now, if you take a look at the structure, this P-fresh vectorizer has two sub-branches. First one is very similar to the fresh vectorizer, and the other is also very similar except this part. So this P-fresh vectorizer has what? First, processes the input random process Y using the upper branch. Second, it takes the complex conjugate of it and then does the same thing. Here, be careful. This G is not G is not ideal low-pass filter. G is something very strange. And G has what? G has only positive part in the passband. And same here. So G of T is not the ideal low-pass filter with cutoff 1/2T. It's half of it. Only the positive frequency part is in the passband. Now let's see what happens here in the entire structure. Suppose in the frequency domain, you have the signal component of Y of T that is between 0 and 1/2T. Now what will happen in the upper branch? In the upper branch, it will pass through probably some center branch and appear, right? What about in the lower part? First, you have to understand what happens to a frequency component when that is conjugated. And it may be helpful to remind the property of Fourier transform, but that is not necessary actually. Just consider a simple complex exponential signal. Anyway, Fourier transform or this frequency component idea all relies on very fine division of the signal. So anyway, each component will look like some complex number times that one. And that complex number may be a random variable, but anyway. Now you take the conjugate. What happens? You know this one. And interestingly, we do not much pay attention to this fact. So if you take the conjugation, what happens? Actually, your original component at F0 after conjugation appears at negative F0. So your original signal component here inside this band 0 to 1 over t now appears here at negative F1. So here at the output of the conjugator, now what you have here. And unfortunately, any shift and this strange positive part filtering will pass you. You are blocked. So what happens? This frequency component only appears one of the upper part, one branch of the upper part only. Got it? So in the same way, you now may consider dividing the entire frequency band into lengths 1 over t subintervals. Now what will happen? This one, that one, so every other frequency band will appear on the upper part, right? And all the other ones will appear in the lower part after conjugated and something like that. Got it? So in that sense, the output is containing all the information of y. Because no signal, no frequency component is removed, right? All the frequency components appear at the output. And each frequency component appears just once. Got it? That's why you may have the inverse system looks like this. And that is not a surprise since you've already seen. So this x is the already p-fresh vectorized version of x, for example, a random process. Now, upper part, you see something similar very to harmonic series representation. You just frequency shift and sum up, right? Then what? Be careful. These components, all the components, not only the upper part, all the components can only reside in this half Nyquist zone. By the way, I remember I named this as the half Nyquist zone. Positive half, but anyway, half Nyquist zone. All the components are defined in the half Nyquist zone. And if you shift them, then and add, you have one component. And here you do the same thing, but again, you conjugate the summation. And sum up, you have original x back. Okay? So in this way, similar to the fresh vectorizer and fresh scalarizer, we have properizing fresh vectorizer and properizing fresh scalarizer. And you may say that, wait a minute, I haven't yet shown whether output of the p-fresh vectorizer gives us really a proper complex random process or not. You are right. So we are left to prove that part. We just proved that this structure of p-fresh vectorizer and p-fresh scalarizer is what? Is an invertible transformation. For any choice of the frequency shift and for any choice of the corresponding half Nyquist zone, as far as your signal is strictly band limited and capital L is chosen so that all the frequency components are filtered, properly filtered by this structure. Got it? And this shows an example of what happens after p-fresh properization. So suppose that you have a deterministic signal with Fourier transform looks like this. Then what you do is that you divide you divide this spectrum into half Nyquist-Jones length subintervals. And you take every other parts and what? This one appears here. That one appears there. And be careful, since you do complex conjugation, what happens? You have your coefficient flipped and conjugated. So this one appears here after conjugation. This one appears there, flipped and conjugated. Okay? Since in this case, the S of f is real, conjugation part is not appearing, even though I wrote here. But anyway, you see the effect of that flipping due to the conjugation. Got it? Now, the last task is what? To show the propriety of the output. So the question is, so here x underscore t, the x vector, is the output of the p-fresh vectorizer with frequency shift 1 over t that corresponds to the cycle period of this improper complex random process x. Got it? So how can you show this? It suffices to show what? Its pseudo-autocorrelation vanishes. Or if I remember correctly, we subtract the mean and covariance, right? So, but in this case, our interest was on the zero mean random process. So anyway, it doesn't matter. So oh, sorry about that. Not mission, but just transposition. So we want to show that under the assumption of zero mean, then its covariance matrix valued covariance function. Here we didn't subtract the mean zero or some zero mean. Anyway, this is always a zero matrix for all choice of T and S. How can we prove it? And the proof is shown somewhere in the paper where it is. Yeah, I believe it here. Yeah. Wise and stationary. Okay, it shows that this p-fresh vectorizer stationarizes and at the same time properizes. Okay, so we assume zero mean, and this one means wise and stationary, and this means proper. Ready? So the theorem, the lemma, no, not this lemma. Sorry about that, not this lemma yet. Okay, where is the lemma? Where is the lemma? Okay. Yeah, it seems this is correct. Okay. So the lemma shows this one. Actually, additionally, for any choice of this frequency shift, amount of frequency shift, as far as it is the integer multiple of the original cycle period of the signal, and which is here assumed t sub 0. Got it? So this lemma is threefold. The first one, this pfresh vectorizer stationarizes the random process. So output is Weiss and stationary vector random process. Second, the output vector random process has zero pseudo autocorrelation. And third, this result holds for your any choice of the like it's drawn as far as capital T corresponds to some integer multiple of your cycle period. Got it? And the proof appears in the appendix. And let's see the appendix. Yeah, and I remember the proof was lengthier than it appeared here, because originally the paper was part 1, part 2 paper, and originally it didn't have any impropriety. But here we had more strict page limit because we squeezed the 2 papers into 1, and we had additional impropriety. So if you read the proof, it would be very hard to follow, actually. But anyway, this is the idea. And let's see why this is true then. Any intuition can we have from our knowledge previously obtained? And actually, that is not that difficult if you remember some interesting result. So probably you remember conjugation gives you some interesting thing when you have a real valued signal. And if you consider its Fourier transform. What happens when you have this assumption of real valuedness of a continuous time signal? So let's consider Fourier transform. Precisely speaking, we are talking about Fourier planetary transform of finite energy. Otherwise, we may not have this inverse Fourier transform's existence guaranteed. So what we do is that we multiply in order to extract what is the frequency component in x of t at frequency f. We multiply its conjugate and integrate. So we basically compute the inner product so that we extract the frequency component in x of t at frequency f. That is the continuous time Fourier transform. And now, what happens when x is real? And x is real means that its conjugation is the same as the original signal for all t. So what we do is that we substitute x conjugate here and see what do we get. Or we may do something else, but let's do this. So let's take the conjugation out. Then here we have again something interesting. What is this one? You multiply x of t and e to the negative j 2 pi ft's conjugate. So you have this property. And this is simply written as x conjugate of negative f. And this holds for all f. So if x is real, then what happens? Then Fourier transform at f is what? Containing the same information at Fourier transform at negative f. So if I draw this one, if I choose f0, then here at negative f0, we have some other value, and this value is x of f0, and that value is supposedly x of negative f0, which is same as x conjugate of f0. Why do I talk about this one? Because improper random process behaves very similar to a real valued signal among all the complex valued signals. Got it? I'm not saying that they are equivalent, or I'm not saying that their behavior is exact, but similar. Got it? So, as you will see in other papers to come in this course, you will see something similar to this one. And what does this mean? See that here? This value and that value are conjugate pairs. So one contains the older information of the other. Something very similar happens for the improper complex random process. So suppose this is the frequency axis, and this is the spectrum. Ordinary power spectral density is always non-negative and has what? Has non-negative real value. But as you remember, to fully understand the spectral correlation, we need symplectic Fourier transform of the autocorrelation function of the random process. Then what happened for Y-sense stationary, Y-sense cyclostationary random process? You had what? You had impulse fancies with spacing equal to the inverse of the cycle period, right? And this was for real Y-sense cyclostationary and proper complex Y-sense cyclostationary random processes. Now, what would be the shape of the bispectrum of improper complex Y-sense cyclostationary random process? And what can we guess from the properizing fresh vectorizer? Because as you remember, this one was not derived precisely in the class meetings, but I said that here is the derivation, and you may understand why this happens by using the fresh vectorizer, right? Because fresh vectorizer gives you what? Y-sense stationary vector value random process. So if you remember correctly, what I did was something like this. So the middle branch, right? The middle branch give you what? Give you a Y-sense stationary band limited random process that has power spectrum appears here, right? And the next branch may give you this part, and the other directions next one will give you the information here. And if you take two branches, then cross correlations, right? So they are the two of the branch outputs are jointly wise and stationary, which means that their joint or cross power spectrum is what? Still, if you apply, if you consider bispectrum, has what? Has diagonal impulse fence, right? Now, let's apply the same idea to the claimed P-fresh vectorizer's output. And let's focus on the upper branch, the upper part of the P-fresh vectorizer. So here, not here, here, just consider outputs marked by X, right? Now you take the center one, and as far as the claim is correct, what happens? The centered one will give you a complex random process, strictly band limited to 0 to 1 over 2t, and y-sense stationary. What does that mean? Y-sense stationarity implies diagonal impulse fence in the bispectrum. So what do you have? You have this one. Got it? So you have this impulse fence from the upper part center branch. What about the neighboring branch? And consider power spectrum. Then you have what? That one, that one, that one, that one, that one, that one. And their heights of these impulse fences would be different depending on what was the autocorrelation function of the original input and depending on its frequency content, right? Now, what if you take two branches from the upper part and compute the cross power spectral density and where they will appear? Anybody? So, for example, if you take the center one and next upper one, then you will have this part, right? So basically, just a second. Am I right? Yeah, I believe so. So the upper branch will give you all this northeast part of the impulse fences. Got it? Now, what about the lower branches? And what about the cross correlation between one branch in the upper part and the other branch, another branch in the lower part? What will happen? And I don't think we have enough time here. Just a second. What can we say here? Yeah. So anyway, so our task is to kind of fill up what kind of impulse fancies we will have in the improper complex random processes. One thing is that since this bispectrum is computed what? From the autocorrelation function, anyway, we will have what? We will have something like this. So we still have impulse fancies with spacing 1 over t. Then you may wonder, hey, what about that impropriety? And that appears here. So this is the double Fourier transform of R x x t s. And you know that this is what? Simply double Fourier transform of the autocorrelation function, which has conjugation. So it reveals that we have one more bispectrum. And here, if we have proper case, it's 0 for all values of xi1, xi2 pair. Got it? However, here we have again some impulse fence thing. Got it? And what do you guess? I told you the improper random process behaves very similar to Y-sense station, the real valued signal. So this frequency component, some F0, has correlation with negative F0 component, which means that you have impulse fence on the opposite kind of northwest, southeast direction, like this. Got it? So this is the shape of the bispectrum, complementary bispectrum of the improper complex random process. So you need 2 figures. Got it? So now, by combining these two, we can say something interesting. So see that? This frequency component F0 has correlation with itself and itself plus integer multiple of 1 over t, right? So frequency component at F0 has correlation, possibly correlation at what? F0 plus L over t. And this one says what? Frequency component at F0 has spectral correlation at negative F0 plus L over t. Got it? So it has kind of double correlations, more correlations, possibly. Got it? That is the difference between the proper complex random process and improper complex random process when they are both cyclostationary. Got it? So you not only have an ordinary bispectrum, you also have complementary or pseudo bispectrum that has impulse fancies with spacing 1 over capital T. But the direction of impulse fence is opposite to that of the original impulse fences here. Got it? Anyway, time's up, and I hope I can make up the second take-home exam soon, not this weekend, soon. So be prepared. Okay, that's all for today.